Hey guys, welcome to this particular video, and in this series today I'm going to be talking about how to interpret machine learning models in public health, and I'm going to be using guidance for disease risk and antimicrobial resistance risk prediction. Now in this video today I'm going to explain some of the parameters that you would that is going to be quite important for you to have in mind, and these parameters are quite important for you to have more clearer interpretation of machine learning models in public health, particularly with respect to antimicrobial resistance risk prediction. Now, in the next video, which I'm going to be dropping as well, I'm also going to be doing hands-on practicals on how you can develop an antimicrobial resistance pipeline, and essentially all the steps and categories of things you need to know to get started with the project. But for the sake of this video, we're going to be doing some kind of explainability for you to have a clear insight on how to interpret some of these models in public health. So let's get started. Right. Now the question now is why interpretation matters in public health machine learning. And I have actually had a course where I did mention in my introduction to machine learning video. You can find it on this channel, where I did mention that interpretation matters because of the fact that it's important to build trust and accountability, right? And remember that what we are looking at is basically how machines learn. And what we want to understand is that it's quite important for you to know that building trust requires that some of these interpretable models, they need to foster confidence among clinicians and public health and the public at large, rather, I would say that. And it's something that ensures ethical deployment of AI in sensitive health context. Now, in terms of informed clinical decisions, understanding model rationale is something that is crucial for most practitioners, and particularly for them to integrate predictions into patient care and help public health interventions responsibly. So think about it as you walking into the healthcare organization, and there are actually some couple of insights that you're reporting, not like say, I won't use insight, but some certain symptoms that you are reporting to the clinician or to the person who is taking care or who is required to provide care. And what this means is that based on those information that you're returning to that particular practitioner, it can actually be used in line with the model, which is now going to predict based on what other people have provided, some of the symptoms other people have reported and the outcomes that it came out to be. Now, what this model is going to do now is that it can help in enhancing their decision making. Do you understand? Instead of delay time for diagnosis, checks and all of that. Basically, the model is going to help in making much more clearer predictions and informing decision making. That is just what why interpretations is really very important and relevant in public. So just think about it beyond the black box accuracy. Most times whenever the accuracy is desirable, there is always a lack of transparency. Whenever there is high accuracy, that's more like everybody is wanting it to be very high. Then that means there is quite lack of transparency in health models, and a lack of transparency in health models can have severe consequences, making interpretability paramount. So these are actually some of the things that we really need to know, and with respect to this. Now, the next thing we're going to actually look at is we're going to look at some of the overviews of interpretable models. Now, there are actually some things we will need to get in contact with, and one of them is logistic regression. And more like in logistic regression, what it does is that it provides some kind of clear probability-based predictions, okay? And we deal with, that's why we talk about interpretable coefficients, that tries to show some kind of feature impact. So we're going to explain much of this in the practicals. Definitely, we'll brush it up in the practicals so that it's going to make a lot of sense. But based on decision tree, what we call tree-based models, some of them, they mimic decision making, clinical decision making with rule-based logic, okay? So they use a rule-based logic, and it's easier for us to visualize it and understand. That's why we say, okay, if it is yes, you go this way. If it's no, you go this way, and all of that. Now, for the random forest, more like an ensemble of decision trees. So it's also part of the decision tree-based models. And what it does is that It's an ensemble of decision trees offering robust predictions while still providing insights into feature importance, okay? Which is something we're going to talk about in our practicals. Now, I think it's very important for us to understand ground truth and some of the predictions. I want to talk about ground truth. What is ground truth? Ground truth is more like the true labels. Okay, so it represents that actual observed outcome in surveillance data, confirmed disease cases, AMR presence, and all of that. So just think about it as you have a data sheet and an Excel data sheet on XLS or wherever that is represented in several rows and columns. And then at the last row, you've got your target where you're now like, okay, this is for X, probably infected, not infected, present, absent, and all of that. So that is the ground truth. That's or more like after diagnosis, you see infected, diagnosed correctly, wrongly, whatever, A, B, whatever type of label, okay, or probably if I call it target, that's another thing we call it, okay, the target. So that's the ground truth, okay, and it's very, very important in making predictions. The ground truth is very relevant in our machine learning predictions. And this is a reality against which our model's predictions are judged. So basically, machine learning will say X, Y, is X test, X train, Y test, Y train. So the Y test and the Y train is usually what the ground truth. That's basically where what the features are predicting. Okay, so crucially, the ground truth can sometimes be imperfect due to data collection limitations and some sort of diagnostic challenges. Of course, yeah. So just like think about it as one of the, what are the things that can actually make somebody to be true negative or true positive, wherever. Okay, so this could be as a limitation in terms of the diagnostic toolkit or whatever thing that might have impeded on the outcome. So it could be data collection, insufficient data collection. We're not able to ask proper questions, and we now assumed based on our outcome data. So those are actually what ground truth is all about. Now, when we talk about the predictions or the best models guess, the model's output for an unseen data point, that's what we known as the model's best guess, because that's usually where we look at the Y breadth. Usually that's when we statistically represent that, the Y breadth, and the Y breadth runs on the X test. Okay, that's output of the X test. That's what has been splitted, and it's more like an estimate of probability or class membership, not a definitive statement of reality. And the gap between the prediction and the ground truth is one thing that informs our model evaluation. Okay, that's why whenever we want to now run our accuracy, we'll see our Y test against our Y breadth, what was predicted from what X test, when the data was split. So these are actually some of the basic things we really need to understand, because there's always a ground truth. Okay, that's a Y test, which is something that is the already known outcome. And essentially, after it has been trained, after the model has been trained, then we'll now use the Y test, the Y breadth, and then use it to check the gap, and whatever thing we get, it's now our best model's guess. And there's something I would need to explain, which is very, very important for anybody who is going into machine learning, and that's what we call the confusion matrix. Okay, so think about the confusion matrix as if you're a student of epidemiology and you're trying to do some kind of surveillance, or there is a disease screening in a community X. Now, there's usually what we call true positives. I'm just going to illustrate that in an empty Word document. I'm just going to actually open this, and I'm actually going to say, now, think about it like there is a kind of a disease screening in your community, and this is a disease screening. Now, based on the disease screening, there are some people that are going to be, we'll call them the true negatives. Okay, I think I'm going to just increase that. Oh, sorry, I'm going to increase that a bit so you can be able to see that. Okay, so we're going to have people who call the true negatives. We'll have people who call the false negative, and then we'll have people that will call the false positive, and people that will call the, okay, I'm just gonna get that correctly, true positive. Okay, yes, so I think I've labeled that clearly. Now, what this means in disease screening is that I think this is properly positioned, or probably positioned above, or whatever. Now, we might call these true negatives, right? So who are true negatives? Now, true negatives are people who are accurately diagnosed to not have the disease, okay? To not have the disease or infection, whatever. So I think I can just put a table up. I can insert a row above, okay? All right, so this is more going to be our negatives, and these are our positives, okay? All right, so I think that works fine. I think I could just contrast the table a bit. Yeah, so I think that's fine. Now, that is what we are going to actually call this. We're going to call these negatives and positives, right? So who are these people? Now, these are the people that we are accurately, that's true negative. So they are truly negative, okay, after screening. Now, who are now the false positive? So they are falsely positive. So this is for Tn. I'm going to say equal to that. This is actually very important in our machine learning process. Now, for false positive, these are what? These are individuals, people who are wrongly diagnosed to have the disease, okay? No, they are wrongly diagnosed to have the disease, okay? So that's what you're going to call them. So we can color that red, okay? No, I think I can color that probably another, I can color that green, okay? So they are quite wrongly classified to have the disease, whereas they don't. That's what we call false positive. They are false positive. They are falsely saying that they're positive. Okay, now that's important. Now the next one we're going to have now is the false negative, and these are people who are wrongly, I can use the same word, they say people who are wrongly diagnosed to not have the disease. Okay, I can say people who have the disease but are identified to not have it. So this is actually a very dangerous group. Okay, I'm gonna say it's a very dangerous group to be in, because it means that these are mixed cases. I'm going to mark it red, and yeah, I think I'm going to mark it red. So false negatives are usually people that are wrongly predicted to have the what? They are wrongly predicted to have the what? The disease. I think I'm going to just skip it here. This is the best place for this to be. And now, what it means now is that for true positives, remember, for false negative, there are people who have the disease, but the prediction is showing that they don't have it, and that's a very dangerous group. It's a very dangerous group. Now, for the true positives, these are, I think I'm going to mark these. I can mark it pink or whatever. Now, the true positives now are people. These are people. That's for the true positives. They were accurately diagnosed to have the disease. Okay, so I think I'm going to color that. I'm going to color that here. So this is what we call this is what we call what? The confusion what? Matrix. So it's very important. Okay, particularly whenever we are doing a binary, we have a binary outcome. a kind of a binary classification based outcome. Okay, outcomes that are present, not absent, yes, no, whatever. So regardless of the model that we're using to train that particular data set, we will definitely get our confusion matrix, and that's what we call the what. That this is what it is exactly, and this is a very, very important step in epidemiological triad for somebody who is coming from the public health background. Quite very, very, very important for you to take massive note of. Now, there's also something we'll come back to this to look at what we call the precision, and then what we'll call the recall score. Okay, of course, we're definitely going to come back to this. This is going to be important, but let us continue at the main time. Okay, so I think we'll start. I just want to know the reason. And so the next one we're going to look at now is what we call accuracy, right? And which is what I talked about. So accuracy. So what it tells us and what it hides. Now, whenever we talk about accuracy, the overall correctness is usually our true positive plus our true negative, all of our true positive plus our true negative plus false positive plus false negative. Okay, so that's more like the true positive over true negative all over every other thing that is there when it is being summed. And one of the things, what does this mean? Now, what it implies now is that for high accuracy, it implies missed cases, particularly in a rare disease. In a rare disease prediction, a model can have high accuracy by simply predicting no disease for everyone, missing or accurate. That's almost more actual cases. Okay. And our context is something that is very, very key. We can say accuracy is useful when classes are balanced, okay? But it's usually misleading when one class is much more smaller than the others. Probably when you have your X and Y values, probably in your, how would I put it? I think I could say when you have your targets, it's important that there is even distribution in the data set. That's usually going to give you more balanced, accuracy and all of that. Now, I think I'm just going to go back to that illustration and just present a formula, which is going to be important when we will be doing our practicals. So the accuracy, remember, it is your true negative plus your true positive all over your true negative plus the sum of your true negative plus your false positive plus your false negative plus true positive. Okay, and that is definitely going to give you your accuracy score. Okay, so yeah, so a high accuracy could be 90%, 99, 95, 98, and all of that. Okay, now we're going to actually look at this other part of it we will call the precision, and we'll go back to the slides. Now, precision in disease prediction is very, very important. And why is it important? Basically, it's important because when the model predicts a disease, right, how often is it right? What precision means is that each time the model says these are the people that have AMR, how much correct is it? Okay, I think I'm just going to give another explanation there. I could say precision, it tells how accurate is the model each time it predicts someone to have the event, or you can call it the disease. Okay, so remember, like I said, these are very, very important terminologies for you as a machine learning engineer in healthcare or whatever, because essentially you need to have a very solid understanding of the interpretation, because it's not just about writing code. You need to know how to interpret these models, these parameters, these figures, and basically it makes a lot of sense. So each time we talk about the precision, we are interested in knowing how accurate is the model each time it predicts someone to have the disease. So in this case, the statistical term could be our TP. That's our TP, true positives, which is for the ones that are accurately predicted to have the disease. Remember, now we'll divide it by the sum of our true positive plus our false positive. So remember, this is it. So our precision is our true positive all over. Remember, this is false positive, people who are wrongly classified to have the disease, whereas they don't. So we're actually going to divide our true positive all over the sum of people who actually have it and people who are wrongly classified to have the disease, whereas they don't. So that is just basically what our precision is all about statistically. So what's actually the impact of low precision? It's just that whenever there is many false positive, it can lead to unnecessary alarm. So it means that we are not really that sure. Our accuracy is dropping in terms of us saying that this person has the disease or the condition of interest. Remember that these assumptions are important for us to make when we have a clear visualization of our confusion matrix. But then it's something very important for you to understand that whenever there is many false positives, it can lead to unnecessary alarm, meaning that means that our precision is not really correct, or there is wasted public resource in the other individuals. And saying that they've got the condition of interest or whatever. Now, another thing that can actually impact it is what resource implications. High precision is vital when interventions are costly, invasive, or when resources are limited. So it means that it's important for us to understand that now it's very important for us to be very accurate whenever we are seeing that this person has the disease, because the interventions are costly. Think about it, because right now, if we now wrongly go and classify somebody that this person has it, then that means it implies that we will now have to spend a lot of money on that. So it's important for our model to be very accurate, and also it's also very important for us to have a very good recall score, which is something I'm going to talk about. Recall score, and that is important, because if we are now saying that we are trying to have a high precision and there is precision bias by us now having very high, probably a low precision or probably there's high precision bias because we're not accurately screening them. There could be tendencies for us to now classify somebody as false negative because they have the disease, but we couldn't classify them as true positives. And this is actually very important in machine learning. It's quite very important, and because one of the things we need to understand is that it's basically how we feed in our data to the machine. That is how it makes prediction, and it's quite very imperative for us to take that into account. We're also going to explain this when we are going to build our antimicrobial pipeline, resistance pipeline for in practical. So resource implications is something to take account of. High precision is very vital because it's very important for us to get it very accurate, else we're going to waste a lot of money and all of that. So now another thing we'll call recall sensitivity in public health is meaning how many real disease cases did the model catch, and this is something that is very significant in our confusion matrix, because here we can say for our recall score, I think I'm going to color that red because of how. So we can actually say how much people, or how much we want to actually understand the magnitude, how much score or how much people we are the model able to predict to have the disease, to catch and predicted to have the disease. Okay, I think that's, yeah, I'm using a very user-friendly illustration. And essentially, the reason why I'm saying this now is because, oh good, how many real disease cases did the model catch? Okay, that is just a very simple thing. And to actually get this insight, it means that our false negative is a very important value, because false negatives are people that have the disease but is strongly saying that they don't have it. So that means we're interested in this. So we can actually now say that that formula is going to be our true positives divided by our false negative plus our true positive. Okay, that's the sum of our false negative and our what? True positive. So this is basically what we need to understand in machine learning. And essentially, this is a very key component of what we're doing. And yeah, basically quite imperative. We need to know how much people were the model able to catch, and did it predict to have the disease. Okay, so basically that is a very, very, very important metrics for you to like have clear understanding of. Okay, and yeah, so we want to know how much people were the model able to catch and predicted to have disease. So this is what we need to get, and essentially that is that gives us a much more clarity on how the explainability of our machine learning model works. So this is a calculation. So outbreak detection. So high recall score is crucial because for early detection of outbreaks and effective surveillance, minimizing the spread of disease, yeah, is quite important. And AMR control is also other antimicrobial resistance control. Anti-AMR prediction, high recall ensures that resistance strains are identified, guiding appropriate treatment. Okay, so we're going to be putting that into practice because these are very, very important in machine learning, public health, and also other fields as well. Anything that deals with learning from data patterns and all of that. Now, another thing that we are going to be looking at after we are done with our confusion matrix, precision, recall score, and all of that, is that we will perform what we call logistic regression coefficient. And this is something I would like to explain. Now, think about this as when you have now predicted, you've got your features and you've got your targets, okay? Now, basically what the model does is that the model uses the features to train uses the features, right, to predict the targets. And what it means is that it's important for us to use, because we are working with sometimes we work with logistic regression, which is trying to know using numerical estimates as usual, which is what we are using. It is very important for us to understand the direction and the strength of the effect, okay, that the model is predicting or whatever. And that is where logistic regression coefficient comes in, because for us to know the direction, we can use negative or positive, right? And what we mean here now is that positive coefficients indicates that the features increase the probability of the outcome. So I could actually say this way. I think I've done an illustration, but I think this is going to make more sense in practicals. But let's just go back there. And assuming I'm to create a table, probably I could just create a table. And here I have age, I have gender, and probably I think I can just add another cell to the right or whatever. And here I have water contact. And this is the target. What we call the target now is the infection status. Okay, that would be yes, it could be no, it could be yes. Okay, and basically this is what we have, right? And now we have age here. We can have 78, we can have 1,000 years, 100 years if that's disease. We can have 12. We can have gender here, male. We can have male again. We can have female. Water contact can be measured. Now look at the measurement of water contact could be between maybe 1 to 10. That's how much water contact you have in a day. That's water contact per week. Okay, let's assume that's a scale that we're using, and we can say here, here is 1, here is 9, here is 2. Okay, right, all right. Now basically what we are trying to talk about in terms of the coefficient is that we want to understand. Okay, so I think I can color that yellow. So what we're trying to do now is that we're trying to understand how some of these features here, because these are the features, okay, these are what we call features, is that these are what we use in predicting the outcome of that infection. So I'm just going to color that red. Okay, so we use this to predict this, right? Probably sometime when we split this data set, then we'll now use this to predict this. Now, what are we trying to say is that at the end of the day, we might have something like a coefficient table here, which is what I'm going to explain. Here, we can have something like coefficients, and probably I could call it the feature, and then we'll have something we call the coefficient. And what this is going to be here now is going to be age. This could be gender, right? And this could be water contact. Okay, yeah, it can be anyhow. Okay, let me just arrange it because sometimes I could be very logical. Why did I put that here? And all of that. And now basically what this coefficient does, usually we use it usually for more like non-tree based models, okay, like linear logistic regression and all of that, sort of vector machines. Then it could be K-nearest neighbors and all that. So, but that's by the way. What we could do for the coefficient here now, it could be that the coefficient is minus 0.99, for example. It could be this is 2.9933, and this is minus 0.1. Now 0.1. Okay, 000 and all of that. Okay. I could just add another 0 so it looks more presentable. Now, what this coefficient illustrates in our machine learning process is that what we are trying to talk about essentially is that each time there is a positive coefficient rather, it indicates that feature increases the probability of the outcome. And now in this case here, we could say that because this is positive, it means that gender increases the probability of what? Infection. Highly increases it because it's what? Positive. Now, let me assume I've got something like maybe let's say marital status, and I have something like 0.11 or 0.011, 0.022 or something like that. Now, between gender is positive, this is positive as well. So what it means is that marital status slightly increases the risk of what? Infection, because there is usually something we call the number line. When you look at the number line, I could just check out that online. I could just search the number line, okay. And when I check out, when we look at the number line, okay, I could look for an image, and yes, I think this works. So using this as an example, as a perfect illustration, I can copy that. Sorry, let me copy that, and yeah, bring it into our Word document. Okay, good. Now, when we look at the number line, you will see that 0.02 is definitely going to be around this point, right? Compared to 3.3, which is going to be around this point. So what it means is that marital status increases, right? Anything on the positive is on what? It increases the probability of what? This what? Outcome. That means if this is AMR, so it increases antimicrobial resistance infection based on that particular what? Output. Now, if it's negative, it does what? It decreases the what? the probability of the infection, and that is what for age we just gave an assumption, and that means it decreases it, and that's 0.099 is going to be around this point. Okay, and now if we have something like, let's assume this is minus 7.10, that's going to be around this point. So that means water contact highly decreases the probability of AMR infection. So that is just a very simple explanation or illustration of logistic regression coefficients, which is very, very important. Just like I said here, negative coefficient suggests the opposite of the relationship, and it means that the magnitude of the coefficient indicates the strength of the association. Okay, and that is based on the number. That's what we mean. Okay, if it has a higher number, that means there is a higher magnitude of effect, kind of, right? And for if it is high, if it is lower, that means there is a slight there is a slight association within the effect. And I want us to also understand that logistic regression provides a clear mathematical basis for why a prediction is made. For example, a 1 unit increase in X is associated with a Y-fold increase in the odds of the disease, which is what I just explained. And the more it increases in X, it's associated with the increase in Y. So you can look at this as the Y and look at this as the X. Why it is increasing here, it's also having a significant increase. If it's decreasing as well, the same thing happens if it's decreasing from here, and this is at 300. Okay, let's say it is coming down like this, for example, and that means here now it's at 200. That means it's at this here coming down and all of that. So the transparency is invaluable for building trust and understanding in public health application. So we're going to actually look at another part of this course, which is the model comparison for public health decision making. And basically what we're going to be talking about here now is that for model comparison for public health decision making, logistic regression is usually best anytime we're trying to understand the transparency and explaining specific risk factors, even with moderate performance. It's usually when it's usually best. For decision support, decision trees is ideal whenever I want to visualize that there is if visualization is something that's of importance to us, or there is a rule-based decision pathway useful in clinical guidelines. And for random forest is one that offers high accuracy and robustness, feature importance, which is something we're going to talk about. Which of the features is more relatively important or shows significant magnitude in terms of the prediction, okay, that's the model prediction. We're also going to illustrate that in practicals, and I still provides good interpretability as well. So say something trade-offs whenever there is balance in interpretability, performance, and there's safety requirements for the specific public health context. So for decision support tools, models are powerful decision support tools. They are not replacements for human expertise or clinical judgment. Some of the things we need to understand. They are just support. Okay, so diagnostics, other normal traditional diagnostic approaches needs to still be done in that case. And I think that is going to be that. We are now going to apply some of these concepts in our practical antimicrobial resistance risk prediction pipeline using real models. So I'm going to see you in our next video where we're going to perform some of these practicals. I'm going to do scaling. I'm also going to do some model optimization. And essentially, there are a lot of things I'm going to do to make it quite clearer and have us understand all of this. So congratulations to you if you've been able to go through this. Interpretation is very important in machine learning, and I'm definitely going to see you in the next video where I'm going to explain all of that. So thank you very much for your time. See you in the next video where we're going to do the AMR pipeline, building a pipeline using antimicrobial resistance dataset. Bye.